What specific problem does the proposed method aim to address in the context of long chain of thought, COT, generation for large language models, LLMs?
The proposed method aims to address the challenges associated with generating long chain of thought, COT, sequences in large language models, LLMs, particularly focusing on improving the stability and effectiveness of reinforcement learning, RL, for long COT generation. Specifically, it tackles issues such as the instability in extending COT length and complexity during RL training, which can hinder the model's reasoning capabilities. To mitigate these challenges, the method introduces a cosine length scaling reward with a repetition penalty, which stabilizes COT growth and encourages emergent reasoning behaviors like branching and backtracking. Additionally, it explores the use of noisy, web-extracted data to enhance the availability of verifiable reward signals, which are crucial for effective RL training. Overall, the method seeks to enhance the performance and reliability of LLMs in complex reasoning tasks by refining the generation of long COTs.
How does the proposed method or algorithm work? Illustrate step by step. Specifically, detail the process of supervised fine-tuning, SFT, and how it is integrated with reinforcement learning, RL, for enhancing long COT generation.
The proposed method for enhancing long chain of thought, COT generation involves a systematic integration of supervised fine-tuning, SFT, followed by reinforcement learning, RL. First, SFT is conducted on a dataset containing pairs of queries and outputs, where the outputs can be either normal or long COT reasoning tokens. This process initializes the model's policy by training it to generate long COTs, which has been shown to improve model accuracy significantly compared to short COTs. After SFT, the model undergoes RL optimization, where a reward function is defined to encourage correct and verifiable reasoning, focusing on the final answer's correctness rather than intermediate steps. The RL process utilizes proximal policy optimization, PPO, to update the model's policy based on the rewards received, allowing the model to refine its long COT generation capabilities further. This two-step approach, first establishing a strong foundation through SFT and then enhancing it with RL, enables the model to achieve higher performance in complex reasoning tasks.
Can you provide a simple yet illustrative example demonstrating how the cosine length scaling reward and repetition penalty function together to stabilize long COT generation? Walk through an example to clarify how these components influence the output.
The cosine length scaling reward and repetition penalty work together to stabilize long chain of thought, COT, generation by incentivizing efficient reasoning while discouraging unnecessary repetition. For instance, consider a model generating a COT for a complex math problem. If the model produces a correct but lengthy COT, the cosine reward function will assign a lower reward to longer correct COTs compared to shorter ones, encouraging the model to optimize its reasoning process. Simultaneously, if the model starts repeating phrases or steps to artificially extend the COT length, the repetition penalty will impose a higher penalty on these repeated tokens, discouraging such behavior. This dual mechanism ensures that the model not only strives for correctness, but also learns to generate concise and coherent reasoning paths, ultimately leading to improved performance and stability in long COT generation. The experiments indicated that using the cosine reward significantly stabilized the length scaling behavior, enhancing the model's overall efficiency and accuracy in downstream tasks.
What are the key theoretical or practical benefits of using the proposed cosine length scaling reward compared to traditional reinforcement learning rewards in generating long COTs?
The proposed cosine length scaling reward offers several key benefits over traditional reinforcement learning rewards in generating long chains of thought, COTs. Firstly, it stabilizes the length scaling behavior of models during reinforcement learning, which is crucial for maintaining training accuracy and improving overall model performance. Secondly, the cosine reward incentivizes efficient use of inference compute by rewarding shorter correct COTs more than longer ones, thus encouraging models to optimize their reasoning processes. Additionally, it imposes penalties on shorter incorrect COTs, prompting the model to extend its thinking time when uncertain, which fosters deeper reasoning. Lastly, the cosine rewards design allows for smoother tuning and adaptability, enhancing the model's ability to learn from complex reasoning tasks effectively, as evidenced by improved performance on downstream tasks.
How was the effectiveness of the proposed method validated? Describe the experimental design, datasets used, and the benchmarks employed to measure performance outcomes.
The effectiveness of the proposed method was validated through a systematic experimental design that involved both supervised fine-tuning, SFT, and reinforcement learning, RL, on large language models, specifically LLMA3. 1-8b and Quen 2.5-7b math. The datasets used included a 7,500 training sample prompt set from the math dataset, which provided verifiable ground truth answers, and a deduplicated subset of WEBINSTRUCT 462K for additional noisy data. Performance outcomes were measured using 4 representative reasoning benchmarks: Math 500, AMY 2024, Theorem QA, and MMLU Pro 1K, which allowed for both in-domain and out-of-domain evaluations. The experiments demonstrated that models initialized with long-caught SFT could achieve significant improvements in accuracy, with RL further enhancing performance, particularly on out-of-distribution benchmarks, thus validating the proposed method's effectiveness. Additionally, the use of a cosine length scaling reward and a repetition penalty was shown to stabilize caught length and improve model performance across these benchmarks.
What limitations did the authors identify regarding the new method, especially concerning the use of noisy verifiable data and its impact on training stability? What suggestions do they offer for future research to address these limitations?
The authors identified several limitations regarding the use of noisy verifiable data, particularly its impact on training stability. They noted that while incorporating diverse data, such as the WebInstruct dataset, improved average performance, the presence of noise in this data could lead to instability in the reinforcement learning (RL) process. Specifically, they found that using a rule-based verifier on unfiltered noisy data resulted in poor performance due to low training accuracy on freeform answers. To address these limitations, the authors suggest future research should focus on developing effective verification signals that can scale without relying heavily on human-designed heuristics, potentially exploring self-supervised approaches in RL verification. They also emphasize the need for more robust training data preparation and stability to enhance the overall effectiveness of long chain-of-thought reasoning in large language models.